Hi, I'm AJ from the Lawrence Hall of Science. In our last week Astrophysics Friday video, we talked about the HR diagram. One of the most important parts of this diagram is called the main sequence. Stars on their main sequence fuse hydrogen into helium at their core. But do stars have an infinite amount of this fuel called hydrogen? Well, the answer is no. So what happens to these stars once they run out of hydrogen? Well, like many things, the later stages of a star's life depend on its initial mass. When a star leaves the main sequence, it enters what's called the post-main sequence stages of its life, where it will fuse heavier elements than hydrogen. When we say heavier elements, what we mean is an element that has more protons and neutrons in its nucleus than other elements. Different things happen to stars of different initial masses on the post-main sequence stage. Astronomers think of the masses of stars in the units of solar masses, which has this symbol here. The mass of our star, the Sun, is 1 solar mass, which is equal to 2 times 10 to the 30 kilograms, which is also equal to 400 trillion elephants. There are 3 categories of initial masses to think about when talking about the post-main sequence stages of a star. The 3 categories are 0.5 to 8 solar masses, 8 solar masses to 25 solar masses, and finally 25 plus solar masses.
Let's talk about the 0.5 to 8 solar mass range first. These stars become giants when they leave the main sequence. When a low-mass star runs out of hydrogen, its core gets smaller, contracting to get hotter in order to fuse helium into heavier elements. This reaction produces more energy than fusing hydrogen. The outer layers of the star expand with this increase in energy, almost like being pushed out, and they also cool down. We can think of the core sort of like a campfire. The campfire is very hot. You'll be nice and warm if you're sitting right next to it, but the farther away you sit away from it, the colder you are. Our sun is currently 4.6 billion years old. When it's about 10 billion years old, it'll expand into a red giant, eating up Mars, Venus, and maybe even Earth. This won't happen for another 4.5 billion years from now, though. So don't worry about getting gobbled up by the sun in your lifetime.
Stars in the lower end of this range, up to about 2 solar masses, experience something called helium flash during their giant phase. Compared to the star's entire lifespan, the flash is very short. It's a process that involves lots and lots of helium being fused into carbon through a nuclear fusion process called the triple alpha process.
After the sun has its helium flash, its radius will shrink back down and it'll fuse helium into carbon and oxygen. After this short period of fusing, the outer layers will expand once again, except this time, it'll definitely reach at least to the Earth's orbit. The outer layers will continue to be blasted away. For a low-mass star, something called a Planetary Nebula is often formed at this point. All that's left of the core will be a stellar remnant about the size of the Earth called a white dwarf.
What's happening here is a case of hydrostatic equilibrium. The red giant turning into the white dwarf is a case of the inward gravity overcoming the outward pressure. Now that we know what happens to low-mass stars such as our Sun, let's think about stars with initial mass of 8 to 25 solar masses.
When these stars run out of hydrogen to fuse into helium, they will soon become supergiants. Many familiar stars we see in the night sky are actually supergiants, like the red supergiant Betelgeuse or the blue supergiant Rigel in the constellation Orion. After helium, the star starts fusing carbon, neon, oxygen, sulfur, and silicon. After each element has fused, it leaves a shell of ash surrounding the core as the next heavier element is fused. It's kind of like babushka dolls, where each time you open one of the dolls, there's a smaller one inside until you get to the very center, the core. Throughout all these fusing stages, the core contracts and expands, and the outer layers do the same. This results in some pretty wacky motions along the HR diagram. Sometimes temperature stays constant and the luminosity increases, and sometimes vice versa. All of this is to maintain the delicate balance of hydrostatic equilibrium for the star. The star would do anything to maintain its internal pressure and gravity.
However, the star runs out of luck once it gets to iron. Fusing iron actually uses up energy rather than create it, stopping the process of fusion. As a result, the star can no longer maintain the high pressures it needs in its core to stay in hydrostatic equilibrium. So, gravity wins and the core begins to collapse, creating what we call a Type II Supernova. As the core collapses, a rebound shock wave is created and it propagates throughout all the layers of the star, giving them energy and breaking them apart. Let's see a little activity on how a star makes energy blow up.
For this activity, you're going to need two bouncy balls. I chose a tennis ball and a basketball. Make sure that the one is bigger than the other. Next, you want to go ahead and bounce each one individually and see what happens. Tennis ball. Now the basketball. Alright, now let's recreate that shockwave effect. To see this, we're going to go ahead and combine both balls by placing one on top of the other, like so. Make sure the smaller one is on top of the bigger one. Next, we're going to go ahead and drop both at the same time and see what happens. Here we go. Whoa! Notice how the big ball barely bounced back up while the smaller ball rocketed up, much higher than you would expect. So how does this work? Well, the energy that the bigger ball would have to bounce back up now gets transferred to the smaller ball, and it has extra energy, making it bounce really, really high. Now you can imagine the dense energetic core of a massive collapsing star sending a huge shockwave effect to the outer layers of the star, giving the outer layers lots and lots of extra energy. What's left behind after an 8 to 25 solar mass star goes supernova is a very dense object called a neutron star. A neutron star has a very small radius. It's only about the size of a city. Imagine the mass of a big star smushed into the volume of an object the size of San Francisco. Wild!
Finally, let's talk about post-main sequence stars that have initial masses greater than 25 solar masses.
Like 8 to 25 solar mass stars, these stars will turn into supergiants after they have left the main sequence. There are a few different ways for them to be supergiants. Some are red supergiants for the rest of the time they're fusing. Others start as red supergiants, then get hotter and turn blue for a while. And others become blue supergiants soon after leaving the main sequence, skipping the red supergiant phase altogether. All of these supermassive stars will fuse heavier and heavier elements until they get to iron and experience a Type II supernova. But when their core collapses, they are often so massive that they collapse to a singularity, a point of infinitely small space but infinitely large mass. This is what we call a black hole. Astrophysicists have yet to determine exactly why supermassive stars collapse to neutron stars, while others collapse to black holes. They may initially think that it has to do with mass, but there is some evidence suggesting that it has to do more with the internal structure of neutron stars. Alas, another great mystery of the universe that you may help solve.
If you've heard of black holes, you probably have lots and lots of questions about them. We'll talk about all the stellar remnants we mentioned today, white dwarfs, neutron stars, and of course black holes in a later video.
We can compare the timelines of the post-main sequence phases for all three initial mass ranges all at once. We see that the higher a star's initial mass is, the less time it spends on the main sequence. All post-main sequence phases are much shorter than the main sequence phase, so the more massive a star is, the shorter its lifespan is. Astronomers like to say that stars live fast and die hard. All stars start out as big balls of mostly hydrogen that spend most of their lives fusing hydrogen into helium. Many heavier elements are fused in the cores of the stars in the post-main sequence stage, such as carbon, nitrogen, oxygen, sodium, magnesium, sulfur, and silicon. No star can fuse the element iron, but very heavy elements like gold are formed in supernovae. Nearly every element on the periodic table gets made in stars. The elements of the periodic table make up all of the stuff in the universe, including you and me. So we can even say that we're made of star stuff.
Alright, well that's all for today. If you enjoyed learning about the later lives of stars, be sure to like this video and follow the Lawrence Hall of Science for more science content. See you later, and keep asking those big questions about the universe.